This is Drax, a coal-fired power plant in England.
Our whole universe was in a hot, criminal state that nearly half a century ago World War II broken, and wait, we learned about nuclear energy, the Alpha Gamma rays, the US launching Manhattan Project, we joined the war, we built two nuclear bombs, uranium, plutonium, unveiling the mystery that all started with the AP chemistry. Hey!
What is nuclear chemistry? It may cause mutations, turn you into a superhero, and feed into the energy of Godzilla. There seems like a lot of bad stuff going on, not to mention the nuclear bombs dropped in Hiroshima and Nagasaki in 1945. But there's also nuclear energy, which we harness in electric production. A mole of nuclear material produces electricity that typically requires tons and tons of coal. And that's why it's such a powerful source of energy. As Fukushima has illustrated, nuclear energy is not without its downsides. In AP Chem, most of the reactions we learned happen on the outermost shell of the atom. Nuclear chemistry looks at the interactions of protons and neutrons. When they're directly involved in nuclear reactions, they release way more energy than the simple transfer or sharing of the outermost electrons. Since the number of protons and neutrons are changing, so is the nature of the reacting element. We call the transformation of elements or isotopes to another element or isotope transmutation, just as valence shells gain or lose electrons in order to lower their energy level. Certain combinations of neutrons and protons make the nucleus more stable. Before we get into the nuts and bolts, like nuclear fission and fusion and why it's so hard to do, we'll first get to know radioactivity.
Our whole universe was in a hot, dense state.
There are three general types of radioactive decay, each of them named after what is released. Uranium-238 is the most common isotope, making up 99% of natural uranium. Uranium-238 then spontaneously decays into thorium-234, and it releases alpha particles. This is called alpha decay, and a particle is just like a helium nucleus, with 2 protons and 2 neutrons. You can see that in the chemical equation. 92 minus 2 is 90, and 238 minus 4 gives you 234. The helium nucleus has a +2 charge, and the thorium atom would have a negative charge. The second type of radioactive decay is beta decay, which simply emits electrons. The thorium-234 from the alpha decay continues to decay on its own, releasing an electron and an atom of xenon. We put a -1 for the atomic number. And then we also have gamma decay, and it's very similar to visible light or UV radiation, but it has a higher frequency and energy. Because it's just energy, gamma radiation has no mass, no protons, no neutrons, or electrons, and is written with 2 zeros. The gamma radiation is released when electrons transition from an unstable excited state to a more stable state that has a lower energy level. Atoms can do this when they are the products of radioactive decay, or if external radiation from other reactions pushes their electrons to a higher energy level. Gamma decay can happen alongside other forms of decay too. From uranium to thorium, for example, it can give up gamma rays as well as alpha particles. Alpha particles have relatively low energy, and they can be stopped by a single sheet of paper. Beta particles have slightly higher energy than alpha radiation, but it can still be stopped by a sheet of aluminum or the surface of your skin. Unlike alpha or beta particles, gamma rays have a much higher energy level, and they can penetrate your skin and ultimately damage your organs within your cells. Exposed to it and you get skin burns, nausea, mutations, cancer, or other radioactive poisoning symptoms. There are 2 types of nuclear reactions. Fissions happen when a heavy nuclei is split into 2 lighter ones, and fusion happens when 2 light nuclei are collided and combined to form a heavier one. We use fission much more often because it is easier to control. Whether for bombs or for power plants, the most commonly used material is uranium-235. By hitting uranium with neutrons from other sources, uranium splits into smaller atoms. One of the reactions may produce krypton-92, barium-141, free neutrons, and lots of energy through the kinetic energy of escaping particles. These particles later transfer their energy into heat energy. Power plants use the heat to convert water into steam, thereby turning the turbines. A uranium atom releases 3 neutrons, which may each hit another uranium atom that releases 3 more neutrons, and the reaction keeps going. Let it run by itself, and you can imagine a chain reaction that adds up pretty quickly. That explains why nuclear weapons are so powerful in uncontrolled situations. We control the reactions with water and nuclear plants, immersing the fuel rods of uranium in water. That obviously is not enough to contain the nuclear reaction since the fuel heats up very quickly. Instead, we use control rods made of material that absorbs neutrons. Insert one of the control rods into the fuel rods. The control rods absorb neutrons and slow the reaction down. If you want more heat, pull the rods out and let more neutrons hit uranium atoms. If you want less, put the rods in to absorb neutrons. The other type of nuclear reaction is nuclear fusion. Fusion reactions produce even more energy compared to the large amounts in nuclear fission. This happens in the sun, involving billions and billions of hydrogen atoms colliding every second. Fusion happens with two hydrogen atoms at high speed colliding to form deuterium, an isotope of hydrogen, releasing positrons and some heat. Another hydrogen collides to form helium-3, releasing gamma radiation this time. Then two helium-3 joins to form helium-4, and two regular hydrogens, also releasing a large amount of energy in the form of radiation. You can see that hydrogen can be reused in the process to start again. The reaction requires 6 hydrogen but produces 2, which means it requires constant refueling of hydrogen. Fusing light nuclei together has a much larger energy change, which explains why fusion is much more powerful than fission. The reaction has to overcome strong natural repulsions between positive charges in the nuclei, so it happens at very high speeds or pressure. At these speeds, the kinetic energy of a particle can produce really high temperatures, something in the 100 million Kelvin range. The material may exist as plasma, and it's very difficult to control such high temperatures for electricity production. It's easy though if you want to make a weapon, since you can just let the reactions run. As you can see, fission and fusions are both great since you produce a lot of energy. Fusion is even better since it only releases helium out of the process and does not contribute to global warming if you want to produce electricity. The question is exactly how are we going to control something of such high temperatures, and how do we contain something so dangerous?
Began to drool, Neanderthals developed tools, we built a wall. We built the pyramids. Math, science, history, unraveling the mystery that all started with a big bang.